In this experiment, we will study on how the size of a product affects its freezing time. Using potato and water as a sample, we will observe their freezing patterns and learn how different factors influence the process. So let's get started. To start the experiment, open the link that given to the virtual experiment. Next, click on the laboratory overview to see the different section, and then select virtual experiment to start. Next, set the initial setting parameters. First, set the starting temperature of the product to 20 degrees Celsius. Next, set the freezing air temperature to -40 degrees Celsius. And set the freezing times at -18 degrees Celsius. Next, to continue the experiment, we will adjust the variables by using the value from the table 3.1 for the sample size and air velocity. First, set the diameter at 5 and the length at 10, and then set the air velocity at 1. Next, choose the product. You can pick either potato or water as your product. Here, I pick potato as my first starting experiment. And then, run the experiment by clicking the experiment start button and let the simulation run and collect the results. After that, you can repeat for the following experiments and export the data to record the data of the freezing times and center temperatures.
In order to plot a graph, first you need to select the time and temperature column. Next, you choose the scatter graph. After that, you need to select data, and then you need to put another data, which is the product water, and the x-axis you put the time data and the temperature data is for y-axis. Next, to make sure your graph looks beautiful, you can put the chart title, the x-axis title, the y-axis title, and also legend, which differentiate which one graph is for potato and which one is for water. Finally, after finish the first graph, you can repeat the next experiment with the same step to make a new graph from experiment 2 until 6.
For part of discussion, question first, discuss how the center temperature change with time for a sample of water and potato. Comment on the shape of the plot. For water, sensible heat is removed because the temperature of water dropped to the freezing point from 20 degrees Celsius to 0 degrees Celsius. At phase change, temperature of water remains at the freezing point until a complete change occurs as latent heat of fusion is removed. From liquid, water converts it into solid ice, causing a rapid temperature drop. The temperature of the ice decreases rapidly as sensible heat removed during the post-freezing period. For potato, the initial temperature decrease is slightly lower than water due to the presence of solute in potato. Ice crystal begin to form is lower than that of water. After supercooling, latent heat is gradually removed with decreasing temperature profile from that of pure water result from concentration in fact during the freezing of foods. Water in potato converts into ice and depress the freezing point. This gradual change in temperature until the potato is mixed of the initial solid food component and ice. The sensible heat is removed until some final pre-selected endpoint temperature is reached. So for shape of the plot, the initial cooling pace of 10 meter per second is faster than 1 meter per second. Highlight the impact of increased air velocity on acceleration heat transfer of 5 millimeter multiply 10 millimeter. At 1 meter per second, cooling is lower and it takes longer to reach steady state temperature. Water cools slightly faster than the potato in the initial phase due to its higher thermal conductivity. While at 10 meter per second, the cooling process is significantly faster for both water and potato. At 1 meter per second, the curves are more gradual, indicating slower heating transfer. At 10 meter per second, the curves are steeper, especially in the early stage, reflected faster heat dissipation. For question 2, discuss the effect of air velocity on the freezing time. When air velocity increases, the freezing time will decrease due to the increase in heat transfer coefficient at increased air velocity. When air velocity is high, the heat transfer coefficient increases, which reduces resistance to heat exchange, also more uniform cooling around the product, minimize temperature variations, and promoting faster freezing. This in fact important during the initial phase of freezing when the surface temperature of the product is relatively high. For larger or irregular shaped product, the effect of air velocity is even more pronounced as it ensures that all surfaces are exposed to consistent cooling. During critical freezing zone, the product converts from liquid to solid. Higher air velocity to remove heat more quickly, reducing the time required for this phase change. The surface of the product to freeze more quickly than the interior, which could affect texture and quality depending on the product. For question 3, use an analytical procedure for calculating freezing time, plain method, and compare the result with those obtained from the experiment. This plain equation for density 998.2 kJ per meter square, latent heat of fusion 335 kJ per kilogram, freezing temperature negative 18 degrees Celsius, freezing air temperature negative 40 degrees Celsius, thermal conductivity 2.24 watt per meter degree Celsius, heat transfer coefficient 15 watt per meter degree Celsius. For water, diameter 5 millimeter, freezing time got 9.51 minutes. For diameter 10 millimeter, got 13.37 minutes. For potato, diameter 5 millimeter, freezing time got 9.08 minutes. For diameter 10 millimeter, freezing time got 12.62 minutes.